In this particular video that you see on the left corner of your screen, you will see that it talks about isomers, and that's the first part of our discussion today, isomers. And that will sort of prime you for organic chemistry if that's the next course that you guys are taking. So,
The molecules methyl isonitrile and acetonitrile have the same molecular formula, C2H3N. However, they differ in the bonding arrangements of the atoms. They are examples of isomers, compounds with the same molecular formula that are not identical. Isomers that have different bonds or differ in the locations of bonds within the molecule are called configurational or structural isomers. Methyl isonitrile and acetonitrile are examples of structural isomers. So also are thiocyanic acid and isothiocyanuric acid. Structural isomerism is very common in organic chemistry. For example, consider the isomers of butanol with molecular formula C4H10O. Normal butanol or N-butyl alcohol consists of a straight chain of 4 carbon atoms with the OH group at the end of the chain. In the isomer that has the common name isobutyl alcohol, the carbon chain is not straight, but has a methyl group bonded to the central carbon of a 3-carbon chain. The alcohol group is still bonded to a carbon at the end of the chain. In secondary butyl alcohol, the OH group is attached to one of the 2 inside carbon atoms in the 4-carbon chain. In tertiary butyl alcohol, the OH group is attached to the central carbon atom, which also contains a methyl group. The 4 butyl alcohols differ in their physical and chemical properties, for example, in their boiling points. Isomers that have the same groups of atoms bonded to one another, but differ in the spatial arrangements of the atoms, are called stereoisomers. In geometrical isomers, the groups are arranged differently with respect to one another. A simple example is cis-trans isomerism about a double bond in alkenes. Because rotation does not occur readily about the carbon-carbon double bond, cis and trans 2-butene are distinct compounds with differing physical properties such as boiling point. Cis-trans isomerism also exists in coordination chemistry, as in this example of cis and trans tetramine dichlorocobalt 3 ion. Optical isomers have the same groups of atoms arranged in the same relationship to one another, but because the molecule lacks a center of symmetry, they are not superimposable upon one another. Optical isomers are mirror images of one another. This example shows secondary butyl alcohol, one of the geometrical isomers of butanol. Notice that all 4 groups attached to the central carbon are different. As a result, the molecule in the foreground is not superimposable on its mirror image. The 2 optical isomers are distinguished by the letters R and S. Molecules such as this are called chiral.
so in this discussion right here, I already told you about the geometries for these compounds, either linear, square, planar, tetrahedral, octahedral. Those are common geometries. The way coordination chemistry um, was discovered or was born was by a few by 2 chemists. One was by Sorfish Jorgensen, that's this guy right here, and Alfred Werner, that's this guy right here. Back in about the 1800s, mid 1800s, they were starting to discover that many chemicals in nature had carbons and hydrogen, and so it gave birth to a class of um, subject or chemistry topic called organic chemistry, because they thought that these chemical came from living things, thereby the name organic. And part of the way organic structures are formed is that the carbons form very, very long chain. And so Jorgensen's thought that these class of compounds that contains transition metal um, elements could also probably form chains. And so his theory for these compounds, he knew what atoms made these compounds. They just didn't know how they were arranged. But what he provided was this, you can see that, okay, this idea that these atoms are connected in a chain like structure. So he proposed that. Werner, on the other hand, did some experiments and he found out that if you've got a cobalt, because they can do chemical analysis, they can take a compound and figure out what the elements are that can make that up. He found out that if you had a cobalt with 3 chlorides and 6 ammonia, that if you put it in water, you can test the conductivity, and the conductivity was proportional to the number of free chlorides. And they could do chloride tests. So when this was put in water, you had 4 total ions that was formed in solution, and 3 of them were chlorides. When he took another chemical, a cobalt with 3 chlorines and 5 waters, what he found out was that you got 3 total ions, and 2 of them were chlorides. When he took cobalt with 3 chlorines and 4 ammonium, then you got 2 total ions, 1 of them was chloride. And finally, when he took another compound, cobalt, 3 chlorines, and 3 ammonia, he found out that there were no ions at all. So this was a puzzle that he sort of thought, and he came up with his theory. He came up with this idea that maybe the ammonia was attached to the cobalt and couldn't be broken when you put it in water, but the chlorides, like sodium chloride, do come off. They would be counter ions. So this was the formula he proposed. He put NH3 in parentheses or in bracket within cobalt and said that the cobalt was directly bonded to this and that the chlorides were counter ions. And so when you dissolve this compound in water, you had a total of 4 ions forming, 3 chlorines and 1 of the cobalt compound. And he came up with this theory because it explained the experimental evidence. Okay. And of course, between these two, Werner and Jorgensen, and at the time Werner was presenting this theory, no one really believed him because they thought that organic chemistry thinking was the correct thought. But once it was proven through experiment, of course, he won the Nobel Prize back in 1913. And Jorgensen, although he made a lot of great contributions to chemistry, you could look him up in organic chemistry, he was really never the same. So that is how coordination chemistry was born by a chemist named Alfred Werner. Okay, Alfred Werner. And today we we believe his theory in terms of coordination chemistry. So this gives rise to ways in which these compounds can form. And so that's why we have isomers. Remember, isomers basically have the same chemical formulas, but because they are arranged in space differently or their connections are different, they have different properties. Just like N2O could be NNO or NON. Structural isomers, compounds with different atomic connection. This would be a structural isomer right there because they have different connection. Coordination sphere isomers. Remember what I told you about the coordination spheres? These are the atoms or the ligands that are directly bonded to the metal. Well, maybe you have different ways those atoms or clusters of atoms are connected to that metal. Well, if they're different within the coordination sphere, then you have something called coordination sphere isomers. Okay, we also have something called linkage isomers, and I'll give you examples of all of these, in which maybe you have one ligand, but it's binding to a different metal. Then we have stereoisomers where it's a higher degree of complexity, and that's because the connection looks very similar between the two isomers, but spatially, in space, they are different. And one of these could be geometric isomers, and the other one, the most complex, is optical isomers. Okay, so we will take a look at each one of these as we go through our discussion. So let's take a look first at structural isomers. Here we have a compound in which we have cobalt, 6 waters, and 3 chlorides. Okay, so in this particular case, here you can see that the waters are bonded to the cobalt, and there are 6 of them, and then the chlorides are counter ions. Remember what counter ions are. They're basically ions outside the coordination sphere, but they're necessary to balance the charge. If the cobalt here is +3, water are neutral ligands, then in order for this to be a neutral molecule, you need 3 chlorides to balance the +3 cobalt. So that's the formula. It's got cobalt, 6 waters, and 3 chlorides. And this compound, if you isolate it, is a violet color. Okay. The next one that has the same formula is, instead of 1 water that is bonded to cobalt, we replace it with a chlorine, and then that water is now a hydrate. Remember what a hydrate is. It's sort of like electrostatically attached to the compound. For those of you in lab, when you made the nickel salts, those were hydrates. So in this particular case, you still had the same formula. You still had the same number of waters, same number of chlorines, and same number of cobalt. So the formulas are identical, except now instead of water, you have chlorine attached to the cobalt. And look what happens to the property. Instead of violet, the chemical was dark green. And there's this third chemical in which 2 of the waters are removed, and these 2 waters are hydrates, and they're replaced by the chlorines. So now all you have is 1 chlorine as a counter ion. This is still a cobalt +3. This is still a cobalt +3 because this chlorine's -1, this chlorine's -1. The charge doesn't change for the ion, for the ligand, just because it's attached to the metal. It's still a -1, and this counter ion's -1 as well. So -3 and a +3 makes this neutral. But look what happens. Instead of this chemical being a dark green, it's now just green. The fact that they all have the same chemical formula, but different ways in which these atoms or ligands or clusters of atoms are attached, makes them isomers. They're also called constitutional isomer. Constitutional. Constitutional isomers just is the way they are connected. Okay, they are connected differently. So let's take a look at the difference between, say, more specifically, uh, linkage isomers. Linkage isomers are like this. You see how this nitro group, this is an NO2 group, this metal right here, and this metal, I believe, is a cobalt, is attached to the nitrogen. And this chemical, it's called a nitro when it's attached to the nitrogen, is sort of like light orange. But you could also have the cobalt not attached to the nitrogen, but one of the oxygens, because remember the oxygens have lone pairs. As long as the element have lone pairs, it can act as a ligand. So here, instead of attaching to the nitrogen, it's attached to the oxygen. It's still NO2. It's called nitrito now because it has a different connection to the metal. But look at the physical property difference. One is sort of a light orange, the other one sort of a dark orange. And yeah, the properties are subtle because the connections are subtle, but it's still a different compound. It'll have um, similar but unique qualities. Okay, so that is a linkage isomer. Whenever you can get a ligand bonded to a different element but still to the same metal, you basically have a linkage isomer. Okay, these ligands right here, this could be bonded to the carbon or nitrogen, this could be bonded to the sulfur or nitrogen, and then there's this chemical right here, 2,2-bipyridine. And the reason why I brought this up again is because actually uh, my research director at Santa Barbara actually discovered this phenomena. Here you have bipyridine. And bipyridine, pyridine, first of all, is an organic compound in which one of the carbons is replaced by a nitrogen group. Okay, all of these are carbons right here. Okay, nitrogen has a lone pair. Bipyridine just means that you have two of these connected in a ring like that. And the nitrogens are generally the atoms that are going to bind the metal. But in this one instant, instead of all three, because this is a bidentate ligand, um, bipyridines binding the metal. See how this is a nitrogen, nitrogen, it binds the metal. This is a nitrogen, nitrogen, binds the metal. But one of the rings actually did a 180-degree flip. And instead of the nitrogen binding the metal, the carbon and the nitrogen binded the metal. So this phenomena was called orthometallation, and it gave rise to all these chemicals that were later used for the optical light emitting diodes. It's that phenomena that gives the metal unique properties to act as diodes, light emitting diodes, that is. So that right there is a linkage isomer. And the reason why it's a linkage isomer is that because of, but for one of these ligands, instead of binding through the nitrogen, which it should have like the rest of these, it binds through the carbon. It's just that subtle difference that can cause um, maybe a property which could be exploited, like what the Japanese did for this compound, and then they made lots of money. Okay, but again, that's what we call a linkage isomer. Carbon bonded versus nitrogen bonded. So here are some of the amazing chemicals that we've made in terms of carbon nitrogen bonds instead of nitrogen nitrogen. And the amazing things about this is that if you shine light on them, they glow. And this one was the original one that we isolated. It was called top green. You can see it's very green. And the reason why it was called top green was because the guy who worked like months and months trying to isolate very small milligrams quantity of this, when he did a chromatography, it was the very top layer. And if you shine a black light on that chromatography apparatus, you can see the green glow. This was the ligand that I work with. I never isolated that, but that was one of the byproducts that I could never get. And then they could change and modify these ligands so that they can get blue and they can get red. They can probably also get orange and yellow. So you have different colors of the spectrum, which gives rise for the ways in which if you put electricity through it, it gives you different colors so that then you can make a monitor or you can put it in an LCD screen. Anyway, let's go back to isomers. This right here is geometric isomers. The difference between what we've talked about so far and these right here is that these connections are all very similar, except now in space they are different. So if you take a look at these right here, they both have chlorines and they both have ammonia, NH3. Okay, so this right here is called the cis isomer. And the reason why it's called cis is because cis means adjacent. Okay, so the chlorines are adjacent to each other. The ammonias are adjacent to each other. That's why it's called a cis. This is an isomer of the cis. You notice it's got two chlorines attached to the cobalt and two ammonias attached to the cobalt. So in this particular case, the atomic connection seems to be similar except for the special spatial arrangement. Here the chlorines are across each other. That's why they're called trans. Trans means across. So this one's called cisplatinum. It's called diamine cis dichloroplatinum 2. So you know it's a oxidation state of +2. This one's called transplatinum diamine trans dichloropplatinum 2. Give you a little history on these compounds. There's a lot of history on these compounds. And I like to share them with you whenever I can because they've changed the world. This particular chemical was one of the first chemotherapy chemical that was used to kill off cancer cells. What they would do is they discovered, this was discovered when people were doing electrodes. They figured that if they put electrode and run electricity through cancer cells, they would kill it. And what happened was it wasn't really destroying the cancer, but there was one instance when they were doing this and they noticed the reduction of the cancer cell. And they did it with other electrodes, and only these types of electrode work in terms of killing cancer cells. So they did an biopsy on the cancer cells, and they found out there was an increase of platinum in these cancer cells, and they discovered that because the electrodes were made out of platinum, there was a chemical there called cisplatinum that was responsible for killing the cancer cell. So back in the early 1960s or thereabout, because that's when this particular chemotherapy agent was used, they started to subscribe cisplatinum to kill off cancer cells, and it worked for a period. But of course, in any chemotherapy, what happens is that you get sick. You it basically poisons you slowly. It not only kills off the cancer cells, it also kills off the healthy cells. But it's it's something that you sacrifice because you really don't want that cancer to grow. Anyway, uh, this gave birth to a whole bunch of research in trying to figure out what other chemicals can do that. So this has historical value, cisplatinum. You could look it up in terms of chemotherapy. So these are called um, geometric isomers. Here's another geometric isomer. This right here is an octahedral geometry. This right here is octahedral geometry. One here is cis, the other one's trans. And it all has to do with how these ligands are placed in the space around the, in this particular case, the platinum. We go into our last type of isomers, and these are called optical isomers. And if the way we introduce optical isomers is by putting a mirror in front of us. If you put a mirror in front of you, what you will see is your reflection. Okay, if you if that particular so optical isomers are basically um, chemicals that might have the same reflection. But when you try and superimpose just means you lay the atom on top of each other to see if they are the correct sequence in space. If you try to superimpose them, you can't. I'll give you a classic example. Take your two hands. Take your left hand and your right hand. And if you take a look at it in front of you, you will see that they are mirror image of each other. Okay, so your hands are kind of like optical isomers because what you can do is when you lay it on top of each other, okay? So put the palm down and take your other hand, put the palm down as well, and you try and lay the middle fingers together so it's aligned. What you find out is that your pinky lines up with the thumb on your left hand, and your thumb lines up with the pinky. Your right thumb aligns with the pinky on your left hand. So they're not superimposable. Okay, you can't put a left-handed glove on a right hand, in other words. That's what we mean by optical isomers. That's what we mean by non-superimposable. They are the same in space, it looks like, but they can't lay on top of each other. And molecules have that property. And in fact, it's so important that optical isomerization that there are certain chemicals with only the correct orientation that will be beneficial for us as a vitamin or as a nutrient, or it may not be beneficial for us. It may even be a poison. Okay? The way you identify optical isomers is you really have to have a good eye for three-dimensional space. When you go into organic chemistry, that's like a critical part. If you go into medicine, if you go into pharmaceuticals, that's very critical. What you do in the beginning, if you really want to identify optical isomers, is you need a modeling kit so that you get used to these things. But there are ways to identify optical isomers. What you do is you have to be able, and when I was taking organic chemistry in college, I remember that you have to be able to take a structure in your mind, be able to rotate it in 360 degrees, and then take that mirror image structure and see whether or not you can superimpose them. Without a model, that's the way you do it. Okay, you got to have a good eye for physical um, substance. But if what you need to do is practice it, and that's why we recommend, if you take organic chemistry, to get yourself a good, um, cheap, doesn't have to be expensive, modeling kit so that you get used to how these things are rotated in space. But it is a very important topic in organic chemistry, and it's a very important topic in medicine, if that's where you guys are going. So again, mirror images. Let me just continue on, and we have so many examples of mirror image in nature. Look at the shells of these things. Okay, one's right-handed, one's left-handed. These things right here, these look identical. Okay, these two chemicals look identical, but they're not superimposable. If you can take this and lay it on top, what you will find is that you have the blue line up together. But you see how this purple sticks out, but this purple sticks back um, in the back. If you rotate this now, let's say we rotate it so that these two are in the same axis. When you rotate this, say 180 degrees, okay, see if you can practice that. What you find out is that now this orange atom is to the left. If you rotate this, let me clear that up real quick so that you guys can see this. So if you, this is sticking out, this is sticking out as well. So this is out of the plane of the board, this is out of the plane of the board. And so if you rotate this 180 degrees, this will be on this side. So now the orange are going to align up and the brown align up, but now this purple atom is in the back of the plane of the board, whereas this one's still in front of the plane of the board. So those are the little exercise that you need to go through if you take organic chemistry. What makes, how you can identify this particular chemical is because one, it's a tetrahedral geometry. and that these four attachments are different. When you have a tetrahedral geometry and the four ligands are unique, then they will always be optical isomers if you make the mirror image. On the other hand, if you have a square planar geometry, let's say I have this metal in the center and I have these four atoms different, they are not optical isomers because I can do this, okay? I'll make the mirror image of this guy. This is my mirror. Remember, this is square planar, okay? It's square planar, so it's flat. What I can do is I can just take this, flip it over 180 degrees, and everything would line up. They would be superimposable. So square planar, four unique ligands on the metal, you cannot get optical isomers. It has to be a tetrahedral geometry. Okay, so yeah, you guys were able to see that in this program called MolView, and I would recommend that program highly if you're taking organic chemistry, because that's a really good. We use that in the lab. It's a really good way of making structures. Anyway, we use that in Chem 152 lab, that is. So let me go ahead and continue on with this. Again, it's just an introduction here, and when you guys get to your upper division course, you hit it more. DNA spirals are optical isomers. Okay, there are so many examples in nature in terms of whenever you have optical isomers, we call these things chiral molecules. Okay, chiral molecules. I know we throw a lot of vocabulary to you. The general umbrella is optical isomers. Once you're talking about organic compounds, then we talk about chiral molecules. Okay, so here is an example of a chiral molecule. This one right here, and its mirror image. And the reason why these are chirals is because these are ligands right here. These are ligands. It's bidentate ligands. Bidentate ligands. So if you could imagine its mirror image, you see how this is pointing up there and then this goes on top and then this goes to the side like that. Well, take that mirror image, pull it out, and then compare it to the real. What you will find out is that they're not superimposable. You need to practice these so that you know that these things are not. But now that you know, when you have tris ethylene diamine, complex, then you will have a optical isomers with that. And you guys did this for those of you in lab. Salt C was a tris chemical. You guys had no way to know whether you isolated one of the optical isomer or the other optical isomers. What generally happens is that you synthesize both, and then it's up to the chemist or someone who's really smart to to separate them apart. Okay, but that's just a lot of pain. You gotta have special equipment for that. So these are optical isomers.
Professor,
Yes.
sorry, can you just explain one more time why that's not superimposable? That
Yeah.
example?
Let me go ahead and do this. Let me clear this up real quick. Okay. So these two are mirror image. Okay. If you take this and you can make a model of it and then bring it out and then sort of lay them on top of each other, what you'll find out is that if you lay this number 2 to number 1, these two will be aligned up right here. Okay, that center atom will be aligned up. This will align up with this, and this will line up with this. In fact, all the four corners will line up. But look at how this connection works. This connection goes from the top to the back, whereas this connection goes from the top to the forward. if you rotate this 100, let's say 90 degrees, so that now this is over here, what happens is that these two comes in front of you, which is not this at all. So you could keep twisting and turning these things so that you try and align these bidentate ligands so that they are superimposable. It's very difficult when we're trying to do it um, in virtually, but if you had a model, what you will find out is that when you rotate this 90 degrees so that these two lines up like this one comes out of alignment. Okay, this one comes out of alignment, and so they're not superimposable.
Okay,
um
thank you.
yeah,
So would we have to like be able to draw up those connections ourselves, or
not at this level, especially since we don't have model kits. You just have to
okay,
recognize, and once you know recognize that when you have a compound like these, that they do have optical isomerization that exists, that's all I we need you to recognize. Okay.
okay,
um,
thank you.
we will you guys will have enough of that if you take organic chemistry. You'll be able to write out, but without molecular models, it's very difficult. What done in the past in my exam when we would meet in class is I would give everyone a molecular model because we have enough of that, and then I would say, okay, make the optical isomers of that, but you guys are saved this semester because we're not meeting in class. So anyway, um, again, an important class of isomers. Here are your tetrahedral again, and again, notice all of these are four different atoms, unique atoms or unique ligands, and if you they're mirror image of each other. Notice how this is in the back, this is in the front, these are on the top, this is behind, behind. So they're mirror image of each other. But now if you take this and bring it over here and actually try and superimpose them, okay, what you find out is that one will be back here and four will be over here. The three and the two will be aligned up, but the four and the one will not. And twist and turn as you may, you will never get them atom per atom superimposed. Now, why are these important? Here are more examples. Okay. Um, like I said, it's important because I don't know if you guys heard about that problem that they had back in the 1960s, right around 1958, 59, 1960. And I was born 1960, so that shows you how old I am. Okay. But back then, there was a morning sickness drug that was used, especially in Europe. It was called thalidomide. And they discovered that, okay, this particular drug was really helpful in helping expected mothers deal with morning sickness. If if someone becomes pregnant, then they become nauseated the first trimester, and that's actually a healthy sign. It means that it's taking the nutrients from the mom and providing it to the fetus, and the fetus will be much more healthy when that happens. That's what I've heard, at least. Okay, the more nauseated the mom is, the more healthier the fetus, at least in the first trimester. But it's very difficult on the mom, so they provide this drug. The doctors subscribe these drugs, especially in Europe, called thalidomide. Now, when it came to the United States, the head of the FDA, the Food and Drug Administrator, his name was Kelsey at the time, said that there's not enough research or clinical studies that says that this thing's going to be beneficial. Plus, we don't know the side effects. So they never pass using it in the United States, which is what's happening today with COVID-19. There, a lot of these drug companies are making these drugs, but we don't know what the side effects are. So we got to be careful, especially because of this landmark case. What happened was that in Europe, and not so much in the United States, unless some of the moms got thalidomide from overseas, was that there was an increase of these flipper babies where their limbs did not grow. And so you had these flipper babies in which they had no arms or their legs were shortened or things like that. And it was a high incident. And the question was, what was going on? And they did research and research and research. And they finally found out that a lot of these mothers who had these deformity babies were prescribed thalidomide, and that was the cause of that. And luckily in the United States, and luckily for my mom as well, because I was in that era, that they never were subscribed that particular drug, and so they didn't have any issues with that. What thalidomide does is that it basically cuts off blood, and so it's actually have a resurgence these days because it helps with cardiovascular disease. But what happens with thalidomide was that one of the isomers was really great to help morning sickness, but the other isomers was deadly. And that was the cause of what happened here. So it's just that little subtlety that can create a poison. And so if you guys ever look it up, it's called thalidomide. And that was a big controversy back in the late 1950s, early 1960s. Okay, but now that drug is making a resurgence because as long as you're not pregnant, it actually has some benefits. Anyway, let me move on. In terms of that, here it is right here. This is the history of thalidomide. Okay, it's a teratogen, which means that Terra means like monster type. Okay, and that's the history of that particular drug. And yeah, I was born in 1960, so if I was in Europe, I could have been one of the victims. Anyway, and I'm sure your parents were probably at that age too. So let's take a look at this real quick.
By the 1950s, researchers had turned some poisons into effective drugs. Natural plant poisons like curare were being used in surgery, and synthetics like nitron mustard were having an impact on cancer. They were just a small part of a new enthusiasm for pharmaceutical products. But in this dash for cash, the authorities overlooked the fact that while poisons can be medicines, medicines can also be poisons. It was only a matter of time before something went badly wrong. Amongst those rushing out new drugs was a German company called Chem. Staffed by many former Nazis, they were searching for lucrative new medicines and had created a chemical that looked particularly interesting. Structurally, the drug was very similar to barbiturates, a class of drug that was then widely being used for anyone who had a sleep disorder. So the company decided to send it off to doctors and get them to try it on their patients who had sleeping problems. The new drug did well and was soon being heavily marketed as effective against insomnia, coughs, colds, and headaches.
Oddly enough, I mean, it was a sedative, but it was also known to be quite useful in morning sickness for pregnant women.
It was distributed initially under the brand name Distaval. By 1960, Distaval was sold throughout Europe, South America, Africa, Canada, and Australia. Around this time, the number of babies being born with deformed or missing limbs and organs, well, they started to rise. Initially just a few, but then the numbers took off. Now, this was clearly really distressing, and something was going on. The problem was the doctors didn't have a clue what. Several traumatic years passed before the cause was finally found, when a young Australian doctor looked at the mothers rather than the babies. The only thing he could find was that these women had all suffered from morning sickness in the early months of their pregnancy, and they had all been prescribed the drug Disavow, which is now more commonly known by its generic name, thalidomide. It has been estimated that around 10,000 babies were severely disabled by thalidomide, half of whom failed to live to adulthood. The situation in America, however, was very different. It was 1960, the year before the link between thalidomide and birth defects would be made. Frances Kelsey was just starting out a new job at the Food and Drug Administration. Her first assignment was to review an application to market thalidomide. Since it was already on sale in the rest of the world, and since no one yet knew that it caused birth defects, it should have been a case of simply approving it. But Kelsey strongly felt the application was not up to standard.
Here's a person who was very well trained in pharmacology and medical practice. And so when she saw the application, she was kind of appalled. It struck her more as testimonials than good, solid clinical research. And she sent a letter responding to the application saying that in its present form, it could not be accepted and to submit additional data.
Another application was submitted to the FDA. But Kelsey was still not convinced by the safety data. So despite mounting pressure from the manufacturer, she again refused thalidomide a license.
There was a back and forth between FDA and the Merrill Company. The Merrill Company was getting quite annoyed, honestly, threatening to go to not only the supervisor, the head of the Bureau of Medicine, but the commissioner of FDA. But she stood her ground. She stood her ground as a scientist. She stood her ground as an FDA official who was, of course, had to uphold the law, and the law required that the drug had to be safe. She persevered through this whole process.
Kelsey continually refused to allow thalidomide a license. When in 1961 the facts finally came out, Americans appreciated just how close they had come to sharing in what was by then a worldwide tragedy. Frances Kelsey was given an award by John F. Kennedy in recognition of her outstanding work.